Hi everyone, in this video we are finally going to talk about stoichiometry. Yay! So for those of you who are not familiar with stoichiometry, beside it being one of the best things about chemistry ever, it essentially is just a way to use dimensional analysis to talk about chemistry. So we use it in the context of chemistry. So all we're doing is using initial numbers to try to predict how much of a certain product we could create, or if we want to create, let's say we want to make 25 grams of a certain product, we could essentially back calculate how much of our reactant we would need in order to do this properly. So the best way to actually discuss stoichiometry is just to work a problem. So let's start off by looking at the combustion of butane. So at this point in the course, I fully expect that you could write out the chemical equation for the combustion of butane. So I'm going to do this for you, but you should be able to do this. So we have butane, C4, multiplied times 2 plus 2. So 4 times 2 is 8, plus 2 would give me 10, plus oxygen. We only discuss complete combustion here. So we're creating CO2 plus H2O. Okay, so now we need to balance it. Always start off with your carbon when we're dealing with combustion reactions. It just makes it easier. We have 4 carbons, so we need to come over here and make 4 carbon dioxides. We have 10 hydrogens, so we need to have 10 hydrogens on the right side. So we can do that by doing 5 times 2. 5 times 2 is 10. Our hydrogens check out. Now we need to look at our oxygens. We have 4 times 2 here. That gives us 8 oxygens plus our 5. 8 plus 5 gives us 13 oxygens. Well, that's a weird number. So we're going to come over here for our oxygen and use 13 halves. That is terrible. Never, ever, ever submit a reaction to me, or excuse me, a chemical equation to me with the coefficient 13 halves. I don't want a fraction. So all you have to do is multiply this whole thing by 2. Okay, so this then becomes 2C4H10 plus 13O2 going to 8 CO2 plus 10 H2O. Always check it. This is the best way to catch mistakes. All right, so 2 times 4, we have 8 carbons on the left side, and then we have 8 carbons on the right side. Now check our hydrogens. 2 times 10, 20 on our left side, and we have 20 on the right side. Now check our oxygens. 8 times 2, that gives me 16, plus 10 is 26. We come over here. 13 times 2 is 26. This chemical equation checks out. Beautiful. All right, now we're ready to do some stoichiometry. Let's say I said we are going to combust 3.3 grams of our butane, and we wanted to figure out what mass of carbon dioxide we could create. And again, let's just put this in grams. All right, so now we're going to use our mole-to-mole ratios in order to determine this out. So we start with what we know. What is unique to this problem? Well, what's unique is that we have 3.3 grams of our butane, so our C4H10. So the first thing we need to do is convert from our grams to our moles. This hasn't changed. It's the same steps as we did before with dimensional analysis. Grams of butane's on the top, grams of butane needs to be at the bottom, so C4H10. If we determine our molar mass, we would see it's about 58 grams per 1 mole of butane. All right, so now we're in moles of butane. Now we're done with butane. We don't want to talk about butane anymore. We're trying to figure out our mass of carbon dioxide. So all we need to do is look at the coefficient in front of the butane, the coefficient in front of the carbon dioxide, and we're going to use this in a mole-to-mole ratio. So all these coefficients are telling me is that for every 2 moles of butane, I will always get 8 moles of carbon dioxide. So we can just use that in our dimensional analysis equation. So we have moles of butane on the top here. We need to put moles of butane on the bottom. We see in our balanced equation that there is a 2 in front of that, so that just goes here at the bottom. Now, we know that for every 2 moles of butane, we have 8 moles of carbon dioxide, so we just type that in. We're not done here. We're trying to get to mass of carbon dioxide. So we have one more step to do. We see that moles of carbon dioxide are on the top, so we need to put moles of carbon dioxide on the bottom. We're converting to grams of carbon dioxide. We know all we need to do is use the molar mass here. So for every 1 mole of carbon dioxide, we have about 44 grams of carbon dioxide. Now, check your units, see if this works out. Grams of butane, cross that out. Moles of butane, cross it out. Moles of carbon dioxide, we're left in grams of carbon dioxide. It looks like our pathway is logical. So solve this out. So 3.3 times 8 times 44 divided by 58 divided by 2. If you do that properly, you should get something of about 10 grams of carbon dioxide. If that doesn't make sense, stop right now and ask questions. All right, now let's move on and let's see if you can actually do one of these problems. So we're going to take it a step further now. If you have 0.85 grams of pentane, okay, so we're going to say 0.85 grams of pentane was combusted. We did a combustion reaction in a calorimeter. These calorimeters are coming back. They're sneaky. Okay. What mass of water was produced? That's it. That's the whole question. You should be able to do this, okay? What mass? And I'm going to lead you. I want it in grams. Go. All right, did you get an answer? Hopefully you did. If you didn't, that's okay. We're going to work through it together. The very first thing you have to do is determine a chemical equation. If you don't determine a chemical equation, you will not be able to do this problem. All right, so we say pentane was combusted. So that gives us all the clues we need. Pentane, pent meaning 5. So C5H. Now we're looking for a saturated alkane. So 5 times 2 plus 2. That gives us 10 plus 2, so that would be 12. C5H12. Plus oxygen, which is O2, creates carbon dioxide plus water, okay? Very generic combustion reaction. Now, we have to balance it. We have 5 carbons on the left side, so we're going to come over here and put a 5 in front of the carbon dioxide. We have 12 hydrogens on the left side, need to come over here. 6 times 2 gives me 12 hydrogens on the right side. Now check our oxygens. 5 times 2 is 10 oxygens plus 6 oxygens. That gives me 16 oxygens. We only have 2 on the other side, but 8 times 2 gives us 16. We're in perfect shape. Check your balanced equation. 5 carbons, so 5 on this side, 5 on this side. 12 hydrogens here, 12 hydrogens here, 16 oxygens here. We have 10 plus 6 gives us 16. That checks. We're good to go. Always, always, always check it. I cannot reiterate that enough. Okay, now we're saying we have 0.85 grams of this, of our pentane. We're trying to figure out the mass of water here, and we want to do this in grams, okay? So all we need to do is go from grams of our pentane to moles of pentane to moles of water back to grams. So start with what you know, what is unique to this problem. 0.85 grams of pentane, C5H12. All right, so now we're in grams, we need to go to moles. So grams of pentane at the bottom, we can go to moles of pentane at the top. We know for every 1 mole, we can just use our molar mass, which is at about 72.15 grams of pentane. Now, we can go up to our chemical equation. For every 1 mole of pentane, we have 6 moles of water. So our mole-to-mole ratio is used here. For every 1 mole of pentane, we have 6 moles of water. Now, we cannot stop here. They didn't ask for moles of water. We asked for grams or mass of water. So we can go from here. For every 1 mole of water, we know we have about 18, I think it's 18.02 grams of water. We just use the molar mass again. All right, check your units. Grams of pentane, moles of pentane, moles of pentane, moles of water, grams of water. Perfect. Multiply it all out, and then we can divide by 72. We end up with the correct answer of 1.27 grams of water. Does that make sense? Hopefully. If not, you need to ask questions. You have to get this down. All right, so now I'm going to take this one step further. We're going to make it even more complicated here. So now, same equation. We're still talking about the combustion of pentane. What mass of pentane is needed? So we're essentially going backwards now. We're doing a back calculation to react with 400 oxygen molecules. So for this example, we're saying we have 400 oxygen molecules in lab. We're trying to determine exactly how much, so in grams, what mass of pentane is needed to fully react with the oxygen molecules. Go. All right, did you get an answer? Hopefully you did, but just in case you didn't, that's completely fine. We're going to work through this together. So the first thing I did was rewrite our chemical equation just for simplicity. A lot of times it's easier to just have it there right in front of your face. All right, so we have to start with what we know or what is unique to this specific problem. So we have 400 oxygen molecules. I'm going to rewrite it just a little bit. 400 molecules of oxygen. That's just how we put it here in our little train track method. We have molecules of oxygen on the top, so we need to put molecules of oxygen on the the bottom. Now, we know we go directly from molecules to moles, so we'll just keep it in oxygen. Now, we know by definition, for every 1 mole of something, we always have 6.02 times 10 to the 23rd molecules. That's Avogadro's number. By definition, that is the ratio. Now, we're in moles of oxygen. We're trying to get to mass of pentane. So we're trying to get to grams of pentane here. We need to go from moles of oxygen to moles of pentane. So we see that for every 8 moles of oxygen, we have 1 mole of pentane. 1 mole of pentane. Now we're in mole of pentane, we're trying to get to mass, so we have one more step. For every 1 mole of pentane, we just use that molar mass. We know we have 72.15 grams of pentane. All right, so now if you calculate that out properly, you should end up with an answer equal to something like 5.99 times 10 to the negative 21 grams, or an answer, something that is really, really teeny tiny, very, very small. So let's check. Does that make sense? Is it possible that if we started out with 400 molecules of oxygen, would that only require a teeny tiny amount of pentane? The answer is absolutely, yes, definitely. 400 molecules of oxygen is a nothing number. That's barely here, just, all right, I sniffed it in. Right, probably not really, but it's a tiny amount. So it does make sense that you would have this incredibly small amount of pentane that is equivalent to that, okay? Always check. Make sure that number makes sense. Okay, now we are done with stoichiometry. At this point, I assume you know how to do these problems forward and backwards. Master this now, because the next video we're taking up even further. It's going to be even harder. If you don't have this down, you're not even going to be able to try to attempt that compta. Take care of yourself, drink water, have a great day.